Okay, so this is the second part of lecture 2 here, and in this part we're going to talk about the normal distribution, right? So now the normal distribution is a very frequently used distribution. It's very common. It's kind of one of the more straightforward ones to use. So let's look at this thing that we call its PDF, right? This kind of ugly looking function. Now the PDF, right, is just defined by this equation. So it's 1 over sigma times square root of 2 pi times e to the minus 1/2 times x minus mu over sigma all squared, right? And so sigma and mu are the standard deviation and the mean of our data set, right? So we could plug this into Excel pretty easily, right? You could say you just give it that equation literally in Excel, and for any x that you plug in, right, you could get a value, and we could come up with a shape and look at the shape of the distribution, right? So the parameters that shape this distribution, they're mu and sigma, right? The mean and the standard deviation. And if we notice, right, there's no skew in this equation, right? There's no skew. And so why? Well, part of that, if we look at, here's a normal distribution. So we've got our observed data plotted as a histogram, and an analytical fit of that distribution is a solid black line here. So let's look. So because a normal distribution is kind of bell-shaped and it's symmetrical by definition, that's why we don't see a skew term in our PDF. So why do we care about this again? So let's just look at our picture here, right? So we've got a histogram of observed data, right? So we've got our histogram of observed data here. And we've got this black line that represents a fit of our mathematical model, right? So here we've taken that PDF, we've given it a mean and a standard deviation, and we've put in a whole bunch of different x's, and what we've come up with is that red line. So where can this be useful? Well, if we look here, right, here we don't have any observed data here over at 4, and we don't really have any observed data over here at -4. But what if we needed to say something at one of these extremes? And now when we think about flooding, where does flooding lie? Flooding tends to lie right here at these extreme ends of the distribution. So if we have no observations, we can't rely on observed data to say something. Instead, we need to fit a mathematical model to the data that we do have and then extrapolate over to these values here, right, using our mathematical model. So that's why fitting these distributions and using these equations is useful. So the cumulative density function, or the CDF, for the normal distribution is given by z is equal to x minus mu over the standard deviation, or big F of z is equal to this ugly integral. And so what are we saying again when we talk about the cumulative density function? Remember, we're talking about accumulating up all the probability, basically, right? And when we talk about that, we're basically saying the area under the curve, right? So remember, anytime we see an integral, right, we're basically summing areas under some curve or something. And so in this case, we're just doing this for the normal distribution. And what we might be interested in is, what's the probability of a value less than some value on our normal distribution, right? And so we might say, oh, it's 80% or it's 60%. And we can find that out by summing the area under that PDF. So let's look at an example here. In a second, we'll look at one example. Okay, so in order to do this, right, we can't normally sum things analytically, right? We can't usually solve this integral by hand. It's tough to do, so instead what we do is we use numerics, right? We use an approximation, numerical approximation. And the question that we're trying to answer, to keep in mind when we're talking about all of this, is how can we move between basically probability space and real space and vice versa? So how can I say, okay, well, what's the flood that occurs 80% of the time, or what's the 80th percentile flood, right? So we're talking about moving, between some probability of occurrence and a value, or some value and what is its probability of occurrence. And in order to do this, right, what we're going to do is we're going to use tables and we're going to use Excel basically to help kind of calculate this CDF, or the area under the curve, to help us build this relationship. And so hopefully we can illustrate that here with 3 examples that we're going to do together. So the first example is very simple, right? In example 1, we're going to assume that the mean is 0 and the standard deviation, it's 1, right? And we want to know what is the probability given x is going to be less than or equal to 1, right? So we want to know what's the probability when for x being equal or less than 1. So in order to do this, we need to use a table here. So here we have our table, right? And we've got these different z values, and and then on the right side of the column next to the z values, the area under the curve, right? So let's think about this in terms of our equation and our distribution. So here we have our normal distribution, and we said we've got a mean of 0 and we've got a standard deviation of 1. So when we're talking about what's the probability for x being less than or equal to 1, what we're talking about is we want to know the area, right, that is less than 1 in our little distribution here. So that whole scribbled in area, right? And the way that we can solve this is we can use that equation on the previous page. So we could say z is equal to, in this case, it would be 1, that's x, minus 0, that would be our mean, divided by the standard deviation, which is equal to 1. So in this case, z would be equal to 1, right? And what we could do is go over here and find where z equals 1 and find the corresponding area. So in this case, we're talking about an area that corresponds to about 84% of our distribution. And what we're trying to, likewise, if we subtract 84% from 1, we would find what the remaining area on the other side of the distribution is. So let's look at example 2 here. In example 2, we're going to assume, again, that the standard deviation is 0 and that sigma, or standard deviation is equal to 1 and the mean is equal to 0. And we want to know in this case, what's the probability of being in between minus 1 and 1? So let's look at our distribution again. In this case, we've got our mean of 0, our standard deviation of 1, sigma 1. And we want to know, here we want to know what's the probability between minus 1 and 1. So we want to know the probability of being in that scribbled in shaded area. So again, we can use our z equation where z is equal to x minus the mean over sigma, or the standard deviation. And so what I'll do is I'm going to allow you guys, after you finish this little lecture for lecture 2, go and complete the example in your course packet here to find out what that area is between minus 1 and 1, or basically the probability of ending up there. And a hint is that you're going to probably have to find 2 cumulative amounts and subtract them from one another. Okay, so our third and final example here for the normal distribution is going to rely on the example straight out of the book. So you can open your textbook, and in this case, we're going to work with the silence data here, right? So I want you to review that. And so this is on page 191. And in this case, what the authors are asking is, what is the 100-year flood flow, right? They want to know what's the 100-year flood flow. And kind of the first hint here is that we need to find z, right? And in order to find z, there's a couple of things that we're going to need to know, right? First thing we need to know is, well, what's the return period here? So we're talking about 100-year flood flow, right? So in this case, we're going to be talking about finding that value. And in the example, they give it as 1 minus 1 over t. So in this case, it's going to be something like 0.99, right? So you're going to want to write that down in your notes. And in order to find z, what they want to do then is they're going to go and they're going to look up in table D2 in the appendices of your textbook. They're going to look up that probability, that area amount from the table, and they're going to be able to back calculate what z is. So in this case, they're going to look up from the table 0.99 area and find what the corresponding z value is. And then they're going to plug it into this equation that we can use to basically solve for that 100-year flood flow. So let's look at what this equation is. It's the mean plus z times the standard deviation of the data, right? And so in the Silets example, they have a bunch of USGS data, and we'll work with this in lab and also in class. And they found the mean of all that data. They found the standard deviation. They looked up the z-value for the 100-year flood event. And what you're able to do then is basically back calculate what the flood flow is for a 100-year event based on the mean and the standard deviation of the data that you have. So again, this goes back to this idea, this concept that if we have some observed data but maybe not enough, we can use a mathematical model such as the normal distribution to basically make an estimate or extrapolate out to values in which we don't have enough raw data to make some inference about, right? So can we go back the other way? Yes, of course we can. What if someone says, well, I want to know what's the return period for a 30,000 CFS flood. So if you go back and think about our cofferdam example, right, from lecture 1, we might ask the question, well, we know that when the river gets so high, it corresponds to a certain flow. So if the river is staged 10 feet, that's about 30,000 CFS, and we know that would overflow our cofferdam. What's the return period of that event? How often does that happen? Does that happen once every 5 years on average? Does that happen once every 100 years on average? So here we can specify what the Q is, and we can back calculate out what Z and the corresponding return period, or T, are. Okay, so that ends this portion. Make sure you fill out your notes, and then we will, in the next little piece of lecture, that's the final part for lecture 2, we'll talk about the gamma distribution.